The Simplyblock Helm chart is used to install the Simplyblock CSI Driver. The CSI Driver consists of two parts, each consisting of a pod with the driver and multiple sidecar containers. The controller part, which can run on any node and performs tasks such as volume provisioning, resizing, snapshotting, and cloning operations via the Simplyblock Web Services API. The node part is required to run on any worker node consuming Kubernetes storage. It connects or disconnects the provisioned PVCs as NVMe volumes to the local Linux host, formats them optionally with a file system, and mounts them into containers. In addition, the Helm chart installs a controller which monitors the provisioning of new worker nodes with certain labels, and depending on the node label, deploys either caching node pods or storage node pods to the nodes. Storage nodes are deployed within a hyper-converged deployment. Different labels are used to indicate a worker nodes, which host primary storage nodes, and worker nodes, which host secondary storage nodes used for HA failover or restarting, migrating storage nodes from failed workers. While both caching nodes and primary storage nodes require that the worker node has local NVMe drives or cloud block storage volumes attached. This is not the case for secondary storage nodes. First, the Kubernetes control plane receives a new PVC. Based on the storage class of the PVC, the Simplyblock CSI Driver controller part becomes active and contacts the Simplyblock control plane to provision a new NVMe over TCP logical volume. The Simplyblock control plane then performs this action via RPC into the storage cluster. Once this is done, the Simplyblock CSI Driver GA node part becomes active. It picks up the new volume and connects it to the Linux host using NVMe CLI. Once the connect is successful, the volume shows up as an NVMe block device such as dev, NVMe 1N1, and the driver formats it with the required file system mounts it into the pod and container, which requested the PVC instead of formatting a file system. It can also mount the raw block device directly. Please note that Simplyblock automatically detaches NVMe drives from the Linux kernel and adds them to the Simplyblock caching node or primary storage node. It is very important that those drives are not busy under Linux because they cannot be claimed otherwise. In particular, they must not be partitioned or mounted. You may use the lsblk command to verify this. A caching node will only claim the first drive found. To select a particular drive for a caching node or include only particular drives for a storage node, format and mount all other NVMe block devices so that they cannot be claimed. Worker nodes must fulfill a few prerequisites to be suited for CSI driver deployment. In particular, the Linux kernel version must be 5 or higher to support the NVMe over TCP protocol. To host caching nodes or hyper-converged storage nodes of any type, only a limited amount of operating systems are currently supported. Rocky from version 9, Red Hat Enterprise Linux from version 9, and Alma Linux from version 9. Also, it is necessary to reserve a certain amount of huge page memory before the storage node or caching node pods can be started. It is usually not a problem to reserve more than the required amount of huge page memory, as the not required part will remain available as system memory to other pods and processes. In the case of caching node, the huge page memory, which has to be reserved, depends entirely on the size of the NVMe cache. The formula is 1 GB plus the 8% of the NVMe size, which is assigned to the cache. Example, if the NVMe device for the cache is 9 TB in size, and all of it is assigned to the cache, the demand in huge page memory is 5 GB. Please note that if less huge page memory is reserved, the NVMe cache will automatically be downsized, even if the underlying NVMe device is bigger. In the case of a primary or secondary storage node, the amount of huge page memory mostly depends on the maximum amount of logical volumes which are to be attached to the node. The minimum demand is around 2 G, and per logical volume, about 8 maybe need to be allocated. The second resource, which requires attention, is the CPU. A particular CPU mask is assigned to the caching node or storage node. This mask, which is set as a parameter in the Helm chart, contains the particular CPU cores or vCPUs, which are used by the caching nodes and storage nodes. While caching nodes can operate with a single vCPU, storage nodes require a minimum of 4 vCPUs. The actual number of cores to be used influences the performance of the system, in particular the IOPS it can achieve. It thus depends on the amount and performance of the underlying NVMe drives, as well as the required target performance of storage relative to compute. There is a more specific session on performance tuning, which gives a more DE edge. If storage performance is a main concern, it is recommended to switch off hyper-threading the hypervisor or instance and use physical cores only. Simplyblock automatically isolates the cores or VCPs assigned so that they are not used by the kernel. If hyperthreading remains turned on, the recommended setup is to isolate pairing VPU for some of the VCP used by Simplyblock. This behavior will allow some of the worker threads in the Simplyblock process to allocate entire cores instead of just hyperthreads. It can be configured in one of the configuration scripts attached. Learn how to apply the knowledge gained during this session in the training sessions on deploying Simplyblock into Kubernetes using the Helm chart and the session on Simplyblock performance tuning.